Good evening. Welcome to the Newton Lecture Series. I'm Susan Giesica, and I work at SCET in Global Engagement. And tonight, Vicki is all the way on the East Coast, so I'm here representing SCET. You're in for an exciting evening. I won't give away all the big introduction, but Annie's here with us, and I think you'll really enjoy her talk. I'm going to turn it over to Amy, who's going to give you all of your typical instruction on what you need to do to, make sure you've signed in for class, but welcome, and we're glad you're here.
Yeah, thank you so much, Susan. Pretty much covered everything. We have a very, very exciting speaker that SCET is very kindly going to introduce for all of us. So please give a hand to SCET, and we'll kick it off. Thank you.
Hi everyone, I'm Saket. I'm a sophomore studying bioengineering in EECS, and it is my greatest pleasure today to introduce Dr. Kritcher. I really wanted to talk about her not just because of the breakthroughs she's made in scientific research, but also because of the implications that these breakthroughs could have on all of our lives. A little bit about Dr. Kritcher. In the early 2000s, she started at Lawrence Livermore National Laboratory as an intern, and went on to complete her postdoctoral research there on the effects of X-rays on plasma. For the last 10 years or so, she's been working on fusion as a potential source of sustainable energy for the future. Specifically, she focuses on inertial confinement fusion, which in very simplified terms is using giant lasers to compress matter and bring it to very high temperatures to simulate the conditions of the sun and generate reactions that can produce energy. Under her leadership, her team has had amazing breakthroughs, including last December in 2022, when they achieved fusion ignition, meaning they created a fusion reaction that released more energy than was initially put into it, proving its viability as a potential source of energy for the future. This is a breakthrough that scientists have been striving for decades. And as a result of her work, she's received numerous awards, not the least of which is being named as one of the 100 most influential people of 2023 by Times. Here to talk more about her work today, it is my greatest pleasure to introduce to you all Dr. Andrea Kritcher.
All right, thank you for that introduction. That was really nice. So I have some slides today to go through a little bit more specifics about what the breakthrough was. And also kind of a big difference here is you might think of innovation in terms of something different than what I'm showing here, which is really big science type innovation. And how does that look when you're trying to translate big science to and collaborate with industry? So I'll be talking about bringing star power to Earth, so the fusion breakthrough that happened recently. So as you all know, you need a problem to solve, to be innovative, and to drive new ventures. And so the problem here that I became interested in at an early age was the climate and also the energy crisis. Obviously, greenhouse gas and climate change are issues with our current source, with a large fraction of our current portfolio. Pollution or long-lived radioactive waste are issues with our traditional nuclear energy, so fission. And we need more clean solutions in addition to solar and wind to meet the increasing demands. Oh, I guess it's not going to show up there. Where are my slides? There they are. So worldwide energy consumption is projected to increase quite a bit by 2040, and we need more clean energy sources to fill this gap. And so it begs the question, does our own sun provide the solution? It's also powered by fusion, and it could be a potential limitless clean source of energy. So for those of you who aren't familiar with what is fusion, it combines two light nuclei into a heavier nucleus, and it releases a huge amount of energy in that process in the form of a helium and also a neutron. And that's basically because the mass of the reactants after the reaction is less than before, and due to E equals mc squared, we convert that mass to energy. So the reason fusion is so challenging as compared to, for example, fission, which is what we do currently, is because getting the two atoms to fuse together requires very extreme conditions, and this is why we're always talking about the conditions at the center of the sun. So to get the deuterium and tritium, so these are isotopes of hydrogen, so the fuel they're forms of hydrogen. And to get them to fuse together, it requires hundreds of millions of degrees to overcome the electrostatic repulsion and to let the strong nuclear force take over. There's no such thing as cold fusion. It requires very hot conditions. And not only that, if you want to fuse a significant amount of material and be able to use that as a potential energy source, you have to get a large enough fraction of material to these conditions, which is almost impossible to do just by doing work on the material. So you actually need to be able to have it be self-sustained or have it heat itself to get to the right conditions for enough material. And so we need extreme pressures to do that in this inertial confinement fusion scheme. And we also need to do it for long enough durations of time. So currently there's two main different types of approaches for controlled fusion. We have magnetic confinement and inertial confinement, and there's different forms other than what I'm showing here of both of these methods. So to be able to reach these extreme conditions and confine them for long enough periods of time, we need giant magnets. This is an example of the ITER, which is a multi-country collaboration to bring this together and multiple billions of dollars for this facility. And then we have things, for example, like the National Ignition Facility in Lawrence Livermore National Laboratory, which is only about an hour east, so come out and see us if you haven't done it. It's the world's biggest laser, and this lets us study one type of inertial confinement fusion. And due to the results that we've had recently at the NIF, we have growing excitement in this type of confinement. So the National Ignition Facility building is the size of 3 football fields. It's the world's biggest laser. It's 2 megajoules of laser energy in the third harmonic at the target chamber center. Here's all the beam lines, 192, coming down and entering a spherical target chamber that's about 10 meters in diameter. Inside of that target chamber sits a 1 centimeter long hollow can. So 1 centimeter out of 10 meters, and then inside of that 1 centimeter long can sits a 2 millimeter size, BB size capsule, and that's where the deuterium and tritium are inside of that capsule. So we take a 2 millimeter size BB capsule and we squeeze it down to something that's half the size of a human hair. So we're taking that material and squeezing it down to extreme temperatures and densities, and that's how we get to the conditions that were needed to achieve ignition. So the breakthrough for various different types of fusion, not just this particular type of fusion, is that we proved that ignition and target gain in a laboratory setting is possible. So that means it is possible to harness fusion energy if you can work through the engineering challenges. So on December 5th, 2022, we reached pressures that were exceeding 2 times the center of the sun, more than 30 quadrillion watts, but for 90 trillionths of a second, and temperatures that exceed 5 times the sun's core. So these are some key numbers here. It's very short time periods, but very extreme power in that time period. So these systems are pulsed. They're not supposed to be continuously operating like a magnetic type system. So what we do is we pulse them at the rate of multiple times a second. And that's how you would get that would translate to a power plant type situation. So here's fusion energy produced in megajoules as a function of date. And each bar on here is an attempt to get ignition. So down here you can't see anything. There actually were shots down there where we tried to do these experiments. And this is the progress that we've been making more recently in the last couple of years. And as you can see, it's nonlinear. It's very accelerated. And the main reason for that is we started to heat the plasma with the fusion itself. So the key here was getting to the right conditions in the experiment. So what the input conditions you ask of, for example, the laser conditions, the target dimensions, the target materials, getting all the details right so that you can start having the fusion reactions heat up the plasma. And that was the big breakthrough, and that's how we're making such fast progress. So this result provided a basis for a new coordinated funded US IFE program. And again, we're still talking about work here done at the National Laboratory, not in industry. So we provided the physics case at the National Ignition Facility. It's a place where we study the physics and prove that it's possible, and also study other things that are relevant for the lab's mission. It was not intended to be optimized for wall plug energy gain, and that's where sort of our industry partners are taking over. So here we have our target that I talked about. We have the lasers coming in. They heat the inside of a can that creates a 3 million degree X-ray bath that heats the outside of that capsule material, and just like a rocket, that material goes out and the rest of the material gets squeezed down to these extreme temperatures and densities. And now we've shown that that process with the right laser definition, the right target definition, and the right dimensions is repeatable. So we can get repeatable ignition. We actually exceeded that in July. But when we talk about target gain here at the NIF, it's not ready to be plugged into the wall. So we have more fusion energy out than laser energy into the target. So now we can start thinking about optimizing different parts of the system, because the laser that we're using is not optimized for a power plant. So the laser to charge the glass in the capacitor bank is 300 megajoules. That gets converted down to 2 megajoules on target. We only couple a little bit of that to our implosion to various reasons. And then, but we get much more out than we put into the target. So each step here could be further optimized. And we're working on pieces of that, and the industry partners are working on other pieces of that. So I was asked to talk about what is the most surprising thing from this result. And I think one of the most surprising things was that we actually got the fuel to ignite. There was quite a bit of criticism that we could actually get to the right conditions with the laser driver energy we had. And as you can see, attempt after attempt after attempt, and things weren't working, can be quite discouraging, because then you start to believe that it will never happen. And in fact, a JSON report of the National Ignition Facility said it was unlike just recently, right before this increase in yield, said that we weren't likely to ever get ignition on the NIF. But we started to do the alpha heating. We started to get more rapid increase of fuel burnup. We didn't know if there would be something else standing in our way. The codes thought we should get to ignition. The codes thought that before. The codes thought that down here. So as you continue to uncover one problem after another, it's continuous working to overcome those problems. And then when you finally get to a point where there's no problems left and things start working, I think for me that was the most surprising part, because you're always kind of skeptical and nervous. And the reason that we were able, as I mentioned, able to get this self-heating is due to innovations in the design, target, and also fabrication of the target itself. So the materials that went into the target and the processes to make the target got better. And also things like the laser efficiency and control got better. So all these things came together to make this work. So what is the impact on industry? Now we're doing all this work in a national laboratory type setting. There was a significant interest in this result by the global fusion industry, not just by people doing inertial confinement fusion, but also the magnetic community. And in fact, I threw a bunch of quotes up here. I don't have to go through all of them, but ITER, the big experiment in France, that's a multi-country collaboration to try to get fusion, to get a fusion plant working in the magnetic confinement scheme. Noted how important this is for fusion energy research. There's other approaches that are doing basically exactly what we're doing, and obviously they're speaking very highly of our achievements because they follow their business model follows our tech almost exactly. And then other approaches like this first light fusion, where it's some combination of both, and they're commenting how important it is. Basically, this result is the first time that we've ever, in a laboratory setting, been able to get a burning plasma and an igniting plasma. And both of those things are needed to have self-sustained energy production from fusion. So how do we move on from here? So we're a national lab. Now the industry is taking off what is our role? So we're continuing to work with the industry to make these advances, and in some cases the IP is shared, and in some cases it's licensed to them. We have expertise at Lawrence Livermore National Laboratory in high gain target design, so that's one of those steps for improving the efficiency that's going to be required. We have expertise in high rep rate laser systems, which, like I said, these things have to be pulsed. Being able to make cost-effective targets. We have a target fabrication area, fuel system delivery, cost, tritium breeding, all of these things, lifetime of all materials, safety and licensing. So in all of these areas, the National Laboratory is planning to continue to work with various companies and industry to move the field forward. And here's an example of something that was envisioned at Lawrence Livermore National Laboratory actually almost 15 or so years ago. Before we got ignition, and the government wanted to wait for ignition before we put significant effort back into this. As I mentioned, some companies are actually directly just using our technology, so the same type of target physics design with improving things like the laser efficiency and higher gain designs, but basically the same concept. Here's an example, long view fusion, combining NIF's laser fusion breakthrough with modern efficient lasers and patented design to replicate the conditions. We have cooperative agreements already going to work directly with these companies, where we will continue to do the design development to try to get higher gain out for a given amount of energy in, so that we can make a test plant something that could look viable. And the result has also led to new investment, new legislation in fusion from the Department of Energy, and increased funding for private companies. So there was always some level of funding for fusion in the private sector. A lot of it was magnetic confinement. So since this result, more has gone into inertial confinement fusion companies. Here's just a list of all the different institutions that are working together between the national laboratories as well as the private companies. There was a White House summit on a bold decadal vision to invest more in fusion research, including inertial fusion energy. Several new reports on this. Private companies and laboratory investment in this area has gone up significantly, and they established a new initiative, kind of like a new program, but not quite, a new initiative at Lawrence Livermore National Laboratory to directly study inertial fusion energy and the challenges that are associated with it. So actually, I work in the inertial confinement fusion program, and that's different from inertial fusion energy. And it's confusing, but we are paid by the Department of Energy and NSA in my program to get high yields and to support the stockpile stewardship program. There's a separate effort that is supported to try to connect these results with inertial fusion energy companies, and the scientists that are involved in inertial fusion energy as well. So there wasn't a separate inertial fusion energy initiative until ignition, and that's what the DOE was waiting for, was that one shot to say, now we're going to invest in inertial fusion energy and the challenges that surround it. So currently now there's $6 billion in the fusion industry, and it's sort of a race to see who gets there first, but it's also a collaborative thing because everyone wants to see this work. So we're sharing things like diagnostic, target designs, converters, et cetera. So the national labs are also collaborating with these new ventures and on the science and the technology to advance the industry. DOE announced a $50 million milestone-based fusion program across several different companies. And this doesn't seem like a lot of money, and it's not, but basically it's the government saying we believe in these companies, and that helps generate funding from the private sector to back these companies. And so that's why it's so important for these companies to receive these types of awards. And our result was also the basis for new investment in S&T for IFE and cooperative agreements. There's a few different programs listed here. Some of them are more geared towards basic science and technology. And then there's also direct ways that you can do research with these companies that we plan to do, haven't started yet, but plan to do. And then in that sense, it would be a shared licensing type of agreement. So we have $3 million in FY22 to reestablish the IFE program. That's the initiative I talked about. We have Infuse money, that's what the acronym stands for, to provide industry access to DOE-funded capabilities like enabling technologies, our materials science information, our diagnostic development, our modeling and simulations, and unique fusion experimental capabilities. And there's also ARPA-E fusion programs, which advance high potential, high impact energy technologies that are maybe too early for the private sector. And we can collaborate directly through CRADAs, where they can pay our salary and we can essentially work for the companies and help advance things like their design. Strategic service partnerships and funding opportunities also come up. And just to put this in a little bit of perspective, with big science, it's quite a large national or global effort, typically. In this case, national, where you have the government laboratories working together with academia and also industry to try to help push new big science technologies forward. And here's kind of a cool similarity or example, which is space exploration. So it started out in a government-funded laboratory in NASA, and the first man on the moon was 1969. And then if you look at what we're doing now with SpaceX, the first commercial mission was in 2013, several decades later. And this was actually founded 3 decades later. And then we have our Starship, where we're starting to do commercial space exploration now in 2024. So the fusion energy is sort of like this, where it's a decadal type of investment, and it's going to require collaboration between, and the government and SpaceX still collaborate. It's going to require continued collaboration between our government and also private sector. But working together, we can help fast track the innovation for fusion energy. And I'll go back to the cool picture. But so what are we doing now when we go into work day after day? What I'm doing in my field of research is trying to improve the fusion energy out for a given amount of laser driver in. So we're trying to improve that efficiency part. So basically, I need to make these bars go up. I need more fusion energy out. And here's an example of one experiment we just did in July, where we got more out than the December experiment. And we have ideas to try to improve this by a factor of 2 or 3 over the next year, and then ideas for longer term improvement. And here's our cool ignition picture. So I guess with that, I try to keep my talk a little bit shorter so I can answer questions. And I will open for questions. Sure.
Amazing.
Who wants to come sit?
Thank you, Andrea, for being here. I think we can kick off our Q&A section with a question that's related to our theme. So as you might know, our theme for this semester is new ventures, and I know that your technology will help create a lot of businesses. So would you please address how other companies are using your technology to create industry advances or new ventures? And I know you kind of touched on this already.
Yeah, so specifically our technology here and the most recent success was exactly how you get the implosion to converge and ignite. And the company Longview is directly following almost exactly our target design and any new advances that we make over the next few years. So that's one example. The other companies, there's a lot of other companies that are similar, but not exactly the same, and they're learning and benchmarking their modeling against our experiments and benchmarking their designs against our experiments. And so there's quite a bit of overlap in the design side. There's also the diagnostic development, laser development, target development, all of which could benefit a variety of different types of fusion industries.
Okay, another question was just, What has surprised you most throughout this experience?
I think you always hope it's going to work, and you have good reason to think it's going to work, but when it actually does work, and it's been so long, and you know, a lot of people gave up on it, you know, we're the last people left standing, kind of, and then it finally worked, and I think that was the most good surprise.
I guess sort of following up on that, when a lot of people gave up, what was the thing that kept you going? What was your internal motivating factor, but also for the whole lab?
So I think that's a really good question. I think it's somewhat of, because you have a good reason to think that you should do something. Everyone has a good physics basis for why they're proposing to do something, but it hasn't worked in the past, and why should it work now? And it's a lot of digging into different reasons, some of which you can simulate, some of which you can't, as to why you think it would work now, and if you think there's a there. So sometimes it's just about getting to the next shot. So I don't know if the whole thing is going to work, but I know if I make this one improvement, it should help, and then we'll go from there. And that actually happened all the way up the curve there. Each one was kind of like that. Oh, is this the end of the road? Let's make this one adjustment we think will help, and then let's see if we can push it further. And now we're in a really good spot because of the self-heating that we didn't know we would be in before. Oh, I'm at the MC. Oh.
If you had all the money to fund your own research, what would you do?
That's a really good question. There are a few companies that I think, you know, this is the only proven method for getting ignition or burning plasma in a laboratory setting, and all methods are trying to do it. For me personally, I would do something similar, but maybe a different type of implosion scheme. There's like direct drive, where you hit the target directly with the lasers. But the key is really getting in there and doing the experiments. And so if you had all the money in the world and you could build a big enough laser and you could do either or, that's what I would do. I think the challenge here is we've been operating on the hairy edge of driver energy that you need to actually get this thing to work. So it's so small, and hydrodynamic instabilities take over. And if you just can make the thing a little bit bigger and a little bit thicker, life gets so much easier and things start to work. So we've been operating on this hairy edge of driver energy in, and then when you start to put more driver energy in, you amplify the energy out. So I'd probably go for like a 10 megajoule laser if I could, and then have it go either direct drive or indirect drive.
Can I ask another question? Yeah. Do you ever find it difficult to convince the federal government to fund you, or even, you know, I'm not sure how the funding structure is, or even the taxpayer, how do you get people excited in order to fund you?
Yeah, that's also a great question. We're continuously under review, and there's like the JSON committee reviews of the program. So we put forth the best case that we can. Luckily, getting funding directly from DOE is not in my job description. I just have to make the science work. But providing the best science case for that, and then letting our kind of senior level management discuss that with DOE and NNSA. I will tell you one thing though, that things that work and things that help much more than any convincing that a person can do are results. And once you get the results, it blows everything else out. So like the JSON report and all those really, really intelligent people that made the best call that they could at the time couldn't have predicted that, and then once you prove it, it's kind of throughout, you know, the rest is history, and they're on board. So Jennifer was really on board and receptive, and I think she still is, and so that's a good sign.
Hi. Well, ever since fusion development, over here.
Oh.
Ever since fusion development started like 8 years ago, there's been that kind of running gag that it's been 30 years away ever since. So what is your take on that with like the achievements in the past 2 years? Is it still another 30 years away? Are we on a good track for that?
I think the physics result is no longer 30 years away. I think that part actually, people used to think that part, ignition, also 30 years away, or 50. I think the number was 50 when I was here at Berkeley. So the engineering challenges that I mentioned are things that, in theory could be straightforward to do, but will require a lot of development. Again, even though we knew how to get to the moon, it took decades to make it commercial. And so, making things cost effective, overcoming the engineering challenges, and also will require higher gain designs. And we don't know if we can get there yet, but we think we can. So I don't like to give numbers for years because I just don't think that's credible, but it's not going to be in the next few years, and I don't think it's going to be in the next 5 years, or probably not even 10, we'll see. But that's my opinion.
Thank you.
Yep.
So I know that there's been a lot of innovations, I guess. Oh yeah. Well, I introduced you, but I'm Saket. I'm doing bioengineering and EECS. I know that there were a lot of innovations that sort of led up to this breakthrough, but I also know that your team made a lot of advancements. So I guess, in your opinion, what was it that made it like your team at that time that was the one that made this breakthrough?
So let's see. You're correct. All the things have to come together, like improving the targets, improving the laser energy, increasing the laser energy, and the target design all need to come together. There are many different designs that we have going at any one given time. And so there are multiple different approaches, not just one that we're looking into. And so obviously this particular target configuration was important for getting to ignition. A lot of the advances, and if you squint, you can kind of think, and you look at a target from the beginning of the NIF to now, it sort of looks like the same target. It's a ball in a hull ROM with lasers going into the ends. But it's really the details that matter, and controlling all of the instabilities and asymmetries, and it really makes or breaks the experiment. And so it's been a long history of learning from the data that we've taken, all of our experimental data, comparing our simulations to the data, finding out where we can be predictive and make changes, and finding out parameter space where we can't be predictive and not going there. And so I think all of the developments that led up to this design were really key, but you also need things like you need clean targets, or else you get mixing and the whole thing is a dud, right? If you shoot material into your hot plasma, it radiates all the energy away, and that can happen if you have a big dust particle on the capsule. So these things are all really, really important. But I also think the specific design hasn't been replicated at this level.
Hi, I'm Diksha. I'm also bioengineering and EECS. I was just wondering, I know you kind of touched on this question, but like you guys worked on the same project for like 10 years without much success for the first, few 7, 8 years. So when do you think it's like the mark to decide, okay, you know what, this is something that's not gonna work. We need to move past it. We need to change like our approach, or this is an approach that's not really feasible. Like, how do you make that decision?
That's a great question too, because we have done that to some campaigns. We have stopped some campaigns. The key here isn't just looking at the yield out, it's all the other diagnostic signatures that come out of the experiments. And it's basically how close you are to getting it to work, and we have metrics for that. So even though the yield hasn't responded, if you get close in like a specific metric or parameter space, you know that making a change in that space is going to be significant. And we have diagnostics that tell us where we are in like, for example, the pressure energy space. So in these experiments, we need energy density. We need to get the plasma hot enough, and we need to get it dense enough and confine it for long enough. And we measure all of those things. And so exactly where you are there for one design versus another design is important. And other diagnostics, like if you notice that you might be mixing already, and you think if you try to push it, you might go over a cliff. So there's a lot of the challenges we deal with here are controlling how spherically you can implode the capsule. So we're doing PDV work on this plasma, and it requires a spherical piston. And if you don't have a spherical piston, pushing down, you can squirt your plasma out to one direction. It's not efficient. And so we measure the symmetry. We also measure the mix. We measure the time-dependent symmetry, which is important. And then the mix, so you get this hydrodynamic mixing at various different interfaces, not just mixing that's seeded by junk on the capsule, but also just Rayleigh-Taylor mixing or other types of instabilities. And we measure those types of things in other focused experiments. So we have clues about which design may or may not work. And some of that relates back to the things we know didn't work in the past. And so it's all kind of like a complete picture of learning.
Thank you for your speech. I'm a junior at Haas. And I have a question regarding the geopolitics and kind of like, are there any countries who also do this type of fusion ignition research? And if yes, what countries are kind of like pushing forward and investing a lot in this field? Thank you.
It's also a really good question, and also because we work at a national laboratory, support the stockpile stewardship program. There are other companies that are interested in pushing this type of tech, some that are allies or friends, and some that are not. But where we are now with our laser technology and the facility that we have, we're ahead. So they can replicate this, but we're probably like a decade ahead in terms of that. And a lot of that IP is controlled.
Just to follow up to that question, how do you decide when to publish or not to? Or what is so in the interest of national security you can't tell people?
Can you say that last part again? I didn't hear that.
You know, yeah, what secrets can you not share with people, and when do you decide that to be open?
Well, I can't tell you that. That's a direct violation. So the ICF program is pretty open, and as you can see, a lot of this work, or maybe you know, has been published. Right now, there are things about the experiments we can't publish, but it's a lot of it's the basic idea is publishable, and then there's IP surrounding things like the laser technology or the target fabrication. But we actually, every time we reach a milestone, there's a publication plan now. So the last ignition result has a plan, again, like the first Lawson criterion paper had back in August 2021. So this will be published in the next month or so. But anytime you kind of get a new big, you hit a key result in terms of fusion energy output, that's something that we publish. And then new physics. So like new physics or new understanding is typically the default if it's not just about the yield.
Hi, I'm Anna. I'm studying chemical engineering. So I wanted to ask, because how it's stated on your timeline, did you come to Cal intending to do a master's first and then stayed for a PhD, or how did that work? Because I know with STEM in particular, there's a lot of various stigmas nowadays with attaining a PhD, going into industry, working at a national lab. What was your experience?
That's a great question. I did come intending to do my PhD because I spent the summer at Livermore before that, and I kind of knew I wanted to be a designer for NIF at that time. That's what I thought I wanted to do. And for that, you have to have a PhD in physics or nuclear engineering. So I did that. Intended to do that. A funny story is I got it from the nuclear engineering department at Cal. My advisor advised me to get a master's because, quote, at the time you might like go run off and have babies, so might as well get your master's now. It was a different time back then. He said it in good jest. So I got it, and it's just another thing you can put on. If I would recommend to do master's versus PhD now, I might have a different opinion on it depending on your career path. If you want to go to a national laboratory and run like radiation hydrodynamic simulations and design NIF experiments, you need it. But to go to industry, you may not. So, and also depending on your exact field of research, it might not be the best use of your time.
All right,
I have a quick follow-up to your previous point. So you mentioned that it was a different time back then. Have you faced any adversity being a woman in STEM, and especially in such, surrounded by such academics? Have you found any adversity, or what has your experience in research been like?
I think just trying to ignore all of the chatter and focusing on the physics is really what my mentality is. And then also I've had a lot of really great mentors. There's not that many women in my field, and somehow I ended up with 2 female mentors, which is kind of amazing. The only 2 in the building, but I ended up with them as my mentors. And that was really important to me because I could sort of see where I might be later in my career, and that was a good peg point for me. And then just like the people I ended up working with were very supportive, and there was no difference. And so I think there can be people that you avoid and can be people that you gravitate towards. I was lucky to find those people, and so I haven't had any issues. And also, he was just joking. I feel bad about saying that, but I did have 3 kids, so there's that.
I had a question. I know you mentioned during your talk that, oh, it's me. You mentioned during your talk that this is kind of a race to who gets to the final technology first, but collaboration is key. So have you ever felt the tension of this challenge in your work, and are there any like tangible ways that you can share, like how so?
Yeah, I was kind of just joking. I think right now it's, so all of the advances that can be made in the different pieces of the problem are welcome to all the problems. And even so, you might want a diversified approach anyways. I've never felt contention because, I mean, partly because I work in a national laboratory, my goal wasn't to make money off of this, as, you know, to just get paid a salary and do cool science, shoot big lasers. But I think at least right now, the response from all the communities has been surprisingly positive, and I've given a lot of several talks to the EATER community. And they're just so encouraging and positive and happy about the result. I think it helps the entire field.
I'm not very into STEM researches, but I'm like very curious. How is like, especially in like your sector and in energy research, what is the percentage of like researches in terms of like money being invested are like government supported and like private money being invested into the research?
Yeah, that's a good question. It's about $6 billion in total, and the government, I think it's like 1 or so. It's like about a half to NIF, and then other various things. And then versus the total energy portfolio, that's like 1.8 trillion. So in terms of the entire portfolio, it's not very much money, and I don't think it's enough to make significant progress. This kind of goes back to the timeline, and they're directly related. So if one issue that we have is the NIF does a lot of other things. It's not, that funding I just mentioned is not all, it's not any of it actually is for energy research. It's just related. It's actually to support the Stockpile Stewardship Program, and that's who funds NIF. And so a lot of the shots that we do at NIF are not, we aren't intending to just bump up the yield or make progress in IFE. And there's actually only kind of a handful of shots, and I think people don't realize this and why so much time between shots happens, between these big high yield shots. We only have like a handful of these attempts on the schedule every year. And if you miss an attempt because of a target failure, you have to wait a few months for the next one. And it's partly just like that's the allocation we have to do those things. So making progress, being able to test an experiment even every single day or like multiple times a second and get that feedback, it would be exponential or more than that growth in terms of how fast we can learn, and would shrink the timeline for how long it will take.
How is your work schedule looks like?
No comment, no. So I have 3 kids. I have a 4-year-old, a 7-year-old, and a 9-year-old. I got that right. And I do try to carve out time for my family. So I work full time, but then I try to take, if I take a Friday off and work on the weekend or something, or work at night after they go to bed. And when I was a graduate student or a postdoc, if you would have told me that, I would have laughed you off. And like, my free time's my free time, but that's kind of how it is now. It's not because I have to, it's because I want to. So
Gotcha.
Call it a hobby.
Congrats.
Thanks.
Just going off what you said earlier about how there's so much time between experiments, the first time in December when it happened, how did you trust the results, and what was that process like?
How did we trust the results?
Yeah.
The results are unambiguous, like in terms of the yield that we got out. We know, we have a lot of detectors to look at the yield, and we have so we measure the neutrons that come out exactly, and we know that, and we do that with several different diagnostics. And then there's other things like you get intense backgrounds on all the other diagnostics, like on the X-ray diagnostics, or like the lights went out in the building. That sort of thing, or like how much, so you blow the target off the end of this long stalk that holds it, and you curl back the arms of the stalk, and that's correlated to the blast. And so you can kind of see like dud, like a little bit more yield, and like, whoa, something big happened on this shot. And that's all like consistent with each other. And even we are reheating the hull ROM, so we heat the hull ROM with lasers. And then when the implosion is so intense, you can actually, as the temperature is starting to cool, you can reheat the whole hull ROM with the implosion, and we see that, and we can correlate that to the yield. So I think we actually know really fairly quickly what the yield is going to be on a given shot. I think the uncertainty was because things can go wrong on a given shot, like if the top of the laser fires differently than the bottom, that can create what we call an odd mode asymmetry. So you can't design your way around that. It just can happen on a shot, and it squirts the plasma out in one direction. And so it's always a nail biter. Am I going to get a mode 1? I don't know. They're doing a lot of work to control it, but at this point, it requires so much precision. And so, or you could have we had some issues recently with, some issues come and go with target fabrication. The can that holds the capsule was flaking material off because a machining process was changed, and a variety of other reasons. It was oxidizing, and some of it fell into the capsule. So for one experiment, we couldn't take the experiment because of that. So it's and we didn't know that until the shot day. So I think being able to get the right conditions on your shot day and having kind of everything work and not misfire or something is what the uncertainty is. But we knew it was a matter of time before we repeated, and now they're doing really good again with the targets.
Quick question. So back into undergraduate and everything, how did you decide that you wanted to major in nuclear engineering? And how was your decision influenced, or did you just go into college just knowing exactly what you wanted to do?
I did not. So I was in Michigan, and I knew I kind of wanted to do something engineering or math related going into undergrad, and I went to the University of Michigan undergrad. So I went to visit campus and kind of looked at civil and mechanical and all the different. I chose nuclear because it was this really small, it was a really small department that was there's all these different things you could study, but it was kind of a small collective department, which I liked at the University of Michigan. Also, it was one of their top departments. I think it was #1 in the country for nuclear engineering at the time, which was impressive. And then also just it had more math and physics than some of the other engineerings, which I was interested in. And so I decided to do nuclear engineering, and I was going to do radiological. It was nuclear engineering and radiological sciences. So I was actually going to eventually become a radiologist to try to cure cancer or treat cancer. And then somehow I just, with your colleagues, and you do these projects together, and you get interested in different things. And I had some colleagues that were all into fusion, and every summer they went out to California and bye-bye snow. And it just sounded so, and they were talking about the National Ignition Facility, and all the different things that the lab had to offer. And that's when I got interested. I came out, and if you haven't been to the lab, it's really an amazing place. It's a mile by a mile, so it's a square mile. And there's like all the different, there's bio, materials, engineering, there's the laser stuff, there's physics. So all these different types of projects you could work on. I just thought that would be a fun place to work. So that's when I decided to go to Berkeley, so I could do my thesis work there and do a PhD.
Hello, my name is Oscar. I'm an X major. And earlier you mentioned that it might take decades before fusion gets commercialized. And what would you say the biggest obstacle for that?
That's a good question. I think developing robust designs that can be, from my area, developing robust designs that can be fielded at high rep rate is the biggest hurdle. We know we can do high rep rate lasers, but high rep rate for these types of experiments, because as I mentioned, they're so hard to do, I think that'll be the biggest challenge. I think the lithium, the tritium lithium breeding thing, that's a massive challenge as well. And so luckily I'm not working on that, but somebody else is in industry.
So you would say it's more technological rather than publicity or economical side? Financial, I mean.
I think financial investment will drive the technology. So that'll drive the rate of technology advances. And so that's really, really important. And the other thing is, like, if you only have one laser and it's aging, and that's the laser you do all your tests on, it's not going to be enough. And so you have to build a facility, which requires money. And I think there's a lot of interest in that. The money isn't there yet to build something else. But I think the publicity hasn't been negative. I know the publicity around fission for other obvious reasons is negative. It produces long-lived radioactive waste, is chances of meltdown. You can't have that here. And so from what I hear from the private companies is the legislation and the licensing that will be required of them is not as bad as they thought, and it's quite reasonable.
Thank you.
Thank you for your talk. I had a quick question kind of following up on the perception or like stigma around nuclear energy in general. Like you briefly mentioned how fission has like Chernobyl and like all these disasters. How do you think that people will be convinced that fusion is safe and it doesn't have all those other concerns? Because people are sometimes irrational about thinking about these things.
Yeah, I think, I think the easiest way to explain it to people is, so for fission, you have all of your material in one location, and it's really easy to start a chain reaction. And so that's why you can have situations where you have large releases of energy and radioactive waste and meltdown. For these experiments, all of your material, all of your fuel the amount of material is so small that if we could burn it all up in one go, we would actually be ecstatic. And it wouldn't be a problem. That would be the ultimate goal. And then the other thing is it's isotopes of hydrogen, and it's so hard to do. You would never be able to get large quantities of for a given driver. You can only get small quantities of mass up to those conditions to do fusion at a given time. And so there's no chance of it just wants to cool itself off immediately after you pulse it, and there's no chance of a runaway type situation.
So, have you ever been offered to work in a private company with a better deal?
I have, yes, and it was a better deal. but the lab has a big laser, so that's... So we'll see. As soon as we get another big laser somewhere, I'm out of here. No, we'll see.
Maybe it's my kind of like Haas thoughts, but like, how do you manage to find equilibrium between like in the decision making when you have like innovation for the world or like money for your family?
Let's see, how do I answer that one? There's a lot of aspects that go into the money question because the salary or the stock might look really attractive for some of these private companies. But it also depends on the long-term market and investment in this area. You have, like, these are really challenging technical problems. Like I said, things that government labs tackle, like space exploration, fusion, and that's why the labs have been able to keep this going for so many decades, because that's the type of project that the labs do really well. I think it's not clear at this point that a private company could just overcome all the hurdles fast enough for the funding. I hope that's not the case. That gets factored into the money versus work satisfaction, I guess, like if I can get to fire the laser versus not. I do think that working for a company is a good option. A lot of people that work at the lab are considering it too, and it's not something I'm ruling out either. I have 3 little kids in school too, and for me that's a factor, so operating them is a factor. Yeah, it's all the life questions rolled into one and what you need in your career at that time.
Gotcha. Thank you.
Yep.
All right, so do we have any final questions? Oh, up there.
Hi, my name's Melissa, and I'm a sophomore majoring in EECS. Thank you so much for your talk, Annie. And since you did go to Berkeley, do you have any fun stories from your time at Berkeley as a master's and PhD student?
Yes, I do. So I know, I don't know which type of stories you're looking for. We had a really small, tight-knit department in nuclear engineering, and I hope it's still the same way. I mean, when I came here, we were all friends. Actually, that's where I met my husband. I'm a big nerd. He was in my research group. He does something different, though, so it's not that weird. But yeah, we used to party on top of the roof of Echeverry, and we would crash the mechanical engineering kegger parties. I don't think they can do that anymore, but you just kind of wander up, and it's like the mechanical engineers have all the fun. But yeah, I think the camaraderie of being there with such a small group and my colleagues, and we would go on trips to Tahoe together. We did a lot of things together. They became like my core group of friends out here. So a lot of good memories from that time.
Yeah, I had one last question. So I know you mentioned a lot about the challenges of getting funding as one of the things you're trying to surmount with achieving ignition. In your opinion, what are the biggest issues with how the government and I guess how society in general allocates funding or chooses which research projects deserve more note? And if you had it your way, how would you change that?
I definitely think if the government really wants to see the types of advances on the timeline they want to see them, we need more funding. I think the private sector is actually more responsive than you might have guessed, and you see people putting in hundreds of millions of dollars, one person to a fusion company. So that's really great. I think coordinating the funding into fewer approaches might help as well. But I would like to see a bigger monetary investment from the government. The hurdle right now is not 100% clear to me. I think that they want to see a few more milestones hit in this program and some more progress before we jump on the next thing. But yeah.
Do we have any other final questions? Okay. Up here.
Okay. Go ahead. Okay, thanks. This is a very silly one, but have you watched Oppenheimer?
I did. I loved it. I was like, oh, I know that guy, and I work with that guy, and all the personality stuff is so real. Not in a bad way, but the physics type personalities. I think there's some other kind of key things that I resonated with, particularly, I mean, doing the NIF shots, like every time you do a shot, it's like the way you feel before it happens is really hard to explain. And I could never like explain how I felt. And then I watched Oppenheimer and I was like, that explains it. So like if you watch him before and after the Trinity test, because he'll be like, you know, he said, this is hard on your heart. And he looks like a zombie. He's not moving. But he's like, he just said that, and that's, you basically kind of sit and wait like this, and it's like your heart is pounding. You can almost even like make yourself sick over it. And then like the shot gets delayed, and then your heart pounds for like 20 more hours while you're waiting. And then after the shot, it's like hard to explain how you feel when it goes well. Like again, he just kind of like, the other guy's jumping up and down, and he's just kind of like, you know, it's almost like a shock happiness. I think I was finally happy somebody could show that, like a real actor could show how that looks and convey that emotion. So I was happy about that. But yeah, it was a fun movie. I know people from Los Alamos that were in that were like extras, and yeah, it's a good movie.
Thank you. Yeah, thank you so much for your talk. So I have a question. My home university is in Munich in Germany. And we have a startup in Bavaria called Marvel Fusion, which for sure you know.
Yeah.
But there's also government projects in France conducted on fusion, for example, by the European Union. My question is more, how realistic is it for a startup, for example, to actually succeed in it, or just plan a business case around it? Because the technology takes so much capital and so much research that I sometimes wonder, because, for example, Marvel Fusion is founded by ex-McKinsey people, I think, how this is actually an investor case. Like I go as a business person and maybe someone with a physics degree and say we need capital for building a fusion reactor, which goes to the billions, if not trillions, right?
So the big reactor type things that I'm showing with magnetic and the NIF type situation, those are that level of investment and the most likely to succeed. There's all these, there's several other kind of what we call alternative techniques, and their approach is to try to make it cheaper and not like you have to build a massive facility. So, you know, they have different challenges. I think the Marvel one you're talking about specifically, proton boron fusion, is much more challenging because you have to reach even higher temperatures. And actually, they just recently started putting deuterium, tritium back in because they couldn't get the neutron production. They're trying to do, actually it kind of evolves and changes over time, but they're using ultra short pulse lasers to try to get the intensity to overcome some of the other heating issues, and it's just not as likely to work. I mean, if they can make progress, that's great, but these kind of alternative schemes where they might be cutting the corners on the big, massive facility come with other risks.
Okay, so just as a follow-up, would you say it's therefore quite unrealistic and it's just a good image that you portray, for example, in front of investors about the potential, or?
I don't think I'm supposed to be commenting on specifically which companies will work and won't, and who to invest in, just like being a government employee. But I will say that they have unique challenges that would be major hurdles to overcome.
Okay.
Yeah.
Thank you.
You were quite conservative when talking about your expectations in terms of time range, but I would be interested in how you imagine all-day life after this groundbreaking innovation is going to be out there. There must be something like driving you, like your passion must come from somewhere.
1 second. So I didn't catch the first half of what you said, if you don't mind repeating it. Are you asking what drives me?
Yeah, what drives you and like how you imagine all-day life is going to change.
Imagine all day life?
Our all-day life after this innovation is going to...
Yeah. I think it's hard to explain. I mean, some things you just kind of like, you latch onto a goal and then you like, that's your thing that you like have to do. And it's hard to explain. Like, my husband will ask me, why are you working so hard? Or like, why do you have to do this? And I'm like, I don't know, I just have to do this. And so I think I'm like very goal driven. That's part of my personality. For me specifically, I thought it was a really, really important goal. I thought it was possible. It could benefit a lot of people, and just, I don't know, you have a bad shot, but like you feel bad about it, and then you get up the next morning and the only thing you can think about is like, what went wrong and how can I explain it and how can I fix it? And I don't know, it just kind of like happens, and like you dream about it, and it's just like, it's like an obsession, kind of like you have to achieve this goal. Life after that goal did feel a little bit like, oh, well, what do I do now? For a bit. And then of course my boss said, well, you need to give me like 10 times the yield. So that became a big challenge. I think right now life does seem really interesting, because when I started in this field, there wasn't really any investment in fusion in the private sector. So that opens up a whole new possibility for me, like for my career going forward. And I think that's really interesting. I think if we can tackle all of the engineering challenges and this can become a reality, of course, that's huge for everybody. So I hope that answered your question.
Yeah, definitely.
Just a quick final question. Can you speak a little bit about being Time's 100 Most Innovative? What was that experience like, and how your life changed before and after, if at all?
Yeah, I think it definitely wasn't expected. Like, as a scientist, you don't really expect to be on that type of a list with, I think Drew Barrymore was on that list, and Sam Altman, which is a little bit closer, but yeah, so it wasn't expected. Actually, I was called into an interview. They said a Times reporter wants to interview you, and I said, sure, like make room in my calendar. And I thought it was a normal interview, and then they just said, you made the list. I'm like, what list? I don't. And then they told me, and I was like, oh, that's cool. And then I started looking it up, and I'm like, oh, that's really cool. I went to the gala, and it was pretty interesting to kind of commingle with those, with those people, as well as the other scientists that achieved the award, like the glacier scientist, and they had the vaccine people were there too, and it was a big range of different types of people that were there. And I think just like interacting with them and seeing how they felt about fusion and what drives them, it was a unique experience, that's for sure. And my life before and after, I think I've gotten more in terms of not just the science, but like the investment and like, how are we gonna move forward with this? I've gotten more interest in that, and so I think that's been helpful. And also some of the other companies as well.
Makes sense, thank you.
Okay, I think with that we can wrap it up today. Thank you so much for joining us today. And the quiz password.
Thank you so much, and feel free to come up if you have any questions. Thank you.